Well, it's great to be here, and I want to acknowledge my co-author, Bill Fisher, who designed a lot of the surveys where we got this data from. So I'm going to show a BayesiaLab analysis of EPA's coral reef monitoring data for Puerto Rico. So coral reefs, as we've heard in previous presentations today, provide valued ecosystem services. The structure of the reef provides shoreline protection from storm waves. The complexity of the reef also provides habitat for fishes, refugia, feeding grounds, nurseries, etc. And as Stefan mentioned, reefs are a great source of tourism and recreation. Coral reefs are extreme risk from local and global stressors. Much of the heating of the planet has occurred, I think over 90% in the oceans, and heat waves and acidification as carbon dioxide enters the seawater are only going to increase in the future, with unknown consequences for coral reef systems globally. And they're also facing watershed pollution from the adjacent coastal zone on top of that. So here's a map from NOAA of the coral reef locations in Puerto Rico in pink. And the sites that were sampled are in the black circle. So we have sites within the southern zone of Puerto Rico. So there were 4 predominant taxa that were sampled by EPA: fish species, coral species, that's stony coral, hard coral, sponges, and gorgonians. And gorgonians are the sea fans. They're also known as soft coral. They kind of look like plants, and they wave in the water. Demographic survey approaches were used for the coral reefs. They were colony-based. The measurements that we're looking at include the height of the reefs, footprint, which is kind of looking downwards, the area of the reef, surface area, surface index, and volume, and taxa richness of the reef species. And for fish, the measurements were number and size. So we have 138 total sites for our case study, and they were sampled between 2010 and 2011. As we saw in the previous picture, transects were used for recording data. These were normalized to square meters. Size, area, and volume occupied were calculated from measurements in the transects for corals, gorgonians, and sponges. And the fish biomass was estimated from their recorded length with a conversion function. For our Bayesian networks, we had 2 major phases. One we'll call an exploratory phase, and the second is the clustering phase. Upon importing the data, we discretized with R2 genopt with 3 intervals given the relatively low n value for the data set. The first part of the exploratory phase used distance mapping with Pearson's and mutual information. The second part used a constrained unsupervised network structure, the maximum weight spanning tree, and we varied the coefficient for complexity downwards from 1 by 0.05 intervals until we had a fully connected network. And then we started the clustering, where we clustered each taxon with expectation maximization, and then we did a hierarchical clustering of the clusters that resulted from that. And then we interpreted our clusters based on relationships with manifests, which are the observed coral reef variables and fish variables that were used to construct the clusters. And we also compared them to other manifests in the database that weren't used to construct clusters for interpretation. So upon importing the data and setting up the nodes in BayesiaLab, we use distance mapping, where the nodes are arranged on the screen on the layout of BayesiaLab based on the relationships between each other. And so this one's based on Pearson's correlation, or the R value, and the nodes that are closer together have a positive R value, and the ones that are on the opposite side from one another have a negative R value. And one of the things we noted is that the taxa-specific variables tended to group with one another, where we had fish, coral, sponges, and gorgonians forming their own little clusters on the distance mapping. We also distance mapped with mutual information. So this is a nonlinear measurement of the sensitivity of the nodes to one another. So the distance mapping is based on the strength of the relationships between the nodes. And So stronger nodes are closer to each other, and ones that have a weaker relationship are further apart. And we saw a similar pattern as we saw with the Pearsons, with the different taxa grouping with one another. Another interesting thing we saw was that the coral variables tended to be centered a bit more with the mutual information, indicating that they might have more connections with other taxa than on the other taxa-specific nodes. So our strongest relationships were intraspecific. It's likely the result of interrelatedness among the dimension variables: height, footprint, surface area, and volume. And both linear and nonlinear distance mapping found positive and stronger relationships between sponge and gorgonian variables, negative and weaker relationships between corals and sponge variables, negative and weaker relationships between fish and gorgonians, and the strongest ties were found for coral variables to other taxa for the interspecific relationships. Our second phase of our exploratory analysis used a maximum weight spanning tree. It's considered constrained because it only allows one arc to enter each node. And so it's a good way to look at the strongest connections within a exploratory network structure. And so on the left-hand side, we have our maximum weight spanning tree with our structural coefficient of 1. So this is a balanced structural coefficient, meaning it's balanced between complexity and data representation. And two subnetworks formed. One had the gorgonians and the sponges connected on the top, and the second on the bottom has the coral reef variables and the fish connected with one another. So we lowered the structural coefficient to allow greater complexity when we learned the network until we hit 0.8, and that's when the final connection was made between a gorgonian variable and a coral variable. And interestingly, when we looked at the relationship analysis, all of the relationships had a positive Pearson R value, except for this new learned relationship between the gorgonian and coral variable. And so our final step with the maximum weight spanning tree network with 0.8 structural coefficient was looking at the node force. And the node force is graphically represented by the size of the different nodes in this figure. And basically it tells you the strength of the connections and the number of connections that each node has. And so this is also known as examining the centrality of the nodes. And across the taxa, the height summation and the surface area of gorgonian sponges and corals tended to have the greatest node force. And the fish variables, which you can see extending out to the left, seem to have lower node force within the entire network. So our last phase was looking at clustering. And so we clustered each taxa, each of the different manifests for the taxa individually, with sponges, fish, gorgonians, and corals, each having a cluster with the expectation-maximization algorithm in BayesiaLab. And so first we look at our sponge cluster here, and the percentages represent a relative contribution to that center node, which is a factor node. And each of the states of that factor node are the different clusters that are identified by the algorithm. And so the highest contribution comes from the sponge footprint for the sponge clusters. So we have a few different ways that we use to interpret the sponge clusters. On the left, we have a table representing the posterior means when we condition on each of the cluster states for all the different sponge variables. Green indicates a higher posterior mean value, red indicates a lower, and the row average for that manifest variable is yellow. And on the right, we have a graphical representation of that with a radar plot and normalized values. And we also, for reference, we put the percent of stations that each cluster was associated with at that table at the bottom. So for the sponges, we had C3 with the highest posterior mean values. This means that this had the highest amount of sponges associated with them. C4 had the lowest. Most stations were in C4 and C5 with the low posterior mean values. Only 4.3% were in the high posterior mean value category. Next, we clustered our fish variable. The manifest node with the most influence was the fish biomass per fish measurement. And in this case, we had two clusters with high posterior mean values. Cluster 2 had the biomass high posterior mean values, and cluster 3 had the density and fish taxa richness. Taxa richness is the number of fish species at the site. And when we look at the percent of stations, we see that C2 and C3, the ones with the high posterior means, have only 2.2 and 2.9% of the data respectively. So about 5% of the data are in the high posterior mean values, so have high fish. Next up, we did the gorgonian clusters. The gorgonian footprint had the most influence on the clusters that formed. And our gorgonian clusters, C4 had the highest posterior mean values and C2 had the lowest. And most stations were in C3 and C1, but C4 with the high gorgonians was in 20% of the stations this time. And finally, we have our coral cluster network that was created, and the manifest node that had the highest influence was the mean height of the coral reefs. And we also had different clusters here with high posterior mean values, cluster 1 and cluster 5. Cluster 5 looks like there are sites that have a lot of dense corals, but maybe not very tall corals. The height sum might be from the amount of corals being added up. And cluster 1 tends to be the ones with the large colony forming and branching corals. There's only 3.6% within that category. And C4 is the low coral variables, and over 50% are in C4. So next, we interpreted the clusters further by detaching the factor node with the cluster states for the coral reef clusters and attaching it to the fish variables. So we're kind of looking at the coral clusters as relating to habitat for fish. So here's the network for that. And then we do the same thing, that the C1, 2, 3, 4, 5 at the top of the table are the coral clusters, and the nodes that we're looking at the posterior mean values of are for the fish. And so C1 had the high fish density and fish taxa richness, and coral cluster 3 was associated with high fish biomass and biomass per fish. And if we go back to the coral reef network, C1 had the highest posterior mean values for the coral reefs. So that was the one that had the large branching colonies, and that's associated with high fish density and taxa richness. C4, coral cluster 4, had the lowest posterior mean values for coral, and we can see it's associated with some of the lower values for fish. And C3 and C5 had high taxon richness and density for coral, and C5 had the high height sum posterior mean values for coral. So C3 had some moderate values, and it's associated with the biomass. And we also, if you recall back when we looked at our exploratory analysis, we saw one connection between coral reefs and gorgonians with our maximum weight spanning tree that was negative. And so there might be a competition element that we should look into. So we also attached the coral reef factor node to the gorgonian manifests and did a similar comparison. And we found that C1 had coral cluster 1 had clear low gorgonian values, while C3 to C5 tended to have higher ones. And C1 is, for the corals, associated with the high posterior mean values. So that kind of confirms what we're seeing, where we're seeing either high corals or high gorgonians. And C4 had the lowest for coral. And finally, we connected our fish factor node to all of the other variables that weren't used to construct it, all the different habitat-related variables for gorgonians, sponges, and corals here. And this one was a lot more complex to interpret. Fish C2 is the one with high biomass, and fish cluster 3 has the high density and taxa richness. And those two tended to have the higher coral posterior mean values, but there's a lot of other aspects that have to be interpreted with connecting all these different variables. So we also, now that we have these individual taxa-specific cluster networks, we clustered the clusters themselves and created this hierarchical cluster network. So this center one we call a meta cluster. It's clustering the actual cluster variables, and we can use this for interpreting overall community values with our clusters. And the way that we interpreted our meta clusters was through target optimization trees, just focusing on the taxa-specific clusters. And so the target optimization tree builds a tree by choosing node states that optimize a user function. In this case, we are maximizing meta cluster state 1 in this particular tree here by taking into account the change in a probability and the remaining data, or the joint probability. And the pathways of the tree going downwards contain scenarios where the cluster state is optimally maximized with multiple states of predictor nodes of these different clusters that are attached to it. And the two outputs of interest for us are the highest scoring pathway. And so that's the terminal node that's encased in red instead of in black, or the one that maximizes the probability the most with the most remaining data, and the highest scoring state, or the most influential cluster state in the tree by its position and probability change. So the high scoring pathway for meta cluster 1 contains gorgonian cluster 4 only, and it raises the probability for the meta cluster 1 from 45 to 100%. So that's why it terminates with just one state. And fish cluster 4 scored the highest within this tree, so it had the most influence within this tree. And the gorgonian cluster 4 that we saw in that high scoring pathway was the second highest. So this meta cluster 1 is most associated with high gorgonian, low fish, and low coral posterior mean values. By contrast, meta cluster 3, the highest scoring pathway, contains coral cluster 1, and fish cluster 1 scored the highest in the tree, and fish cluster 1 appears 4 times as these terminal states within the pathways. So meta cluster 3 is most associated with high coral posterior mean values, and moderate values for fish density and taxa richness, but the low fish biomass. And when we removed that joint probability constraints and just allowed it to maximize probabilities within the tree for the states, we saw that it went into a higher value range for the fish density and taxa richness, which was only in 2% of the data. So that was preventing that from being seen in metacluster 3. So clustering of biological variables can provide a community perspective from groups of biological measurements in the environment. Comparing clusters built from one aspect of a data set with another aspect can help interpret the associations between different community groupings. And interpreting cluster in terms of high or low values can also help us to target community types for management. And future research can explore additional characteristics, external variables, and relationships to stressors or human activities with the different clusters. And thank you.